Hello everyone, my name is Yazan and I will present to you our work titled as Near Optimal Trajectory Generation for Flexible Motion Systems using Two-Boundary Approach. In this talk I will explain how to design near optimal trajectories that can control the movement of flexible systems. These trajectories are multi-interval problems that have two boundaries with given terminal conditions. This presentation will cover the following topics. First, we will introduce the problem of controlling flexible motion system and its feed-forward and closed-loop control systems. Then we will focus on the trajectory system dynamics and analyze two common reference trajectories. Next, we will propose a motion trajectory generator system based on singular perturbation theory that can optimize the reference signal and the terminal conditions used. We will also compare our approach with other standard trajectories and suggest some possible extensions. Finally, we will conclude with some remarks. A generic, flexible, and frictionless motion system that moves in only one spatial direction can be approximated as a cascade connection of masses, springs, and dampers, as shown over here. Mathematically, in the frequency domain, its associated dynamics can be given as a transfer function with preferably one dominant rigid mode and a collection of inflexible modes that are usually determined using modal analysis. Each flexible mode has its damping ratio, denoted by zeta, natural frequency, denoted by omega, and a gain denoted by alpha. The overall system has a total mass of mt, an input force denoted by U, and an actual output denoted by PA. Moving to time domain helps exploiting the signals and systems correspondence when designing the motion trajectory system. In this study, we try to discover the appropriate structure of the trajectory generator system that results in minimum tracking error once followed by the companion flexible motion system, denoted here by sigma g. Note that typically in input shaping, a given trajectory signal is shaped based on the known information of the driven motion system without much regard to the generator system of that given reference signal. Having a feed-forward controller denoted here by sigma f and a feedback controller denoted here by sigma c is in fact a common practice in precision motion systems where feed-forward handles almost 99% of the positioning task, while the closed-loop control handles the remaining part including uncertainties, disturbances, and parameter variations. The overall controlled motion system is denoted here by sigma 1, and the trajectory generator system is denoted by sigma 2 with a designated output denoted by PD. Aggregating the dynamics of the controlled motion system results in sigma 1 that is given mathematically as shown over here. Interestingly, the effect of the feedback controller used can now contribute to the definition of the trajectory generator system, whose generated signal PD will enter to sigma 1 through the matrix B shown over here. Similarly, we can write the state space equations for the trajectory generator system sigma 2 as shown over here. We also know that the actual and desired signals depend on the initial conditions and the input signals, so that we can come up with mathematical expressions for both of these signals. At the system level, the tracking error is the difference between the desired input and the actual output, so we need to pick the matrices in sigma 2 to minimize the performance index given here as J. This constitutes the problem statement in this study. In motion control, the desired trajectories can be designed as switched coefficients polynomials. For example, to the left, over here, we see the second-order trajectory that involves three intervals. Note that in it, the jerk signal is infinite, which cannot be physically realized using the available drive amplifiers. Therefore, practically it's avoided. To the right, we have the third-order trajectory that exhibits finite jerk signals, and therefore of practical importance. However, due to its limited number of involved parameters, more than 7 intervals might be needed when the motion system has more than 3 flexible modes to suppress using input shaping techniques, for example. As a result, motion trajectories with higher orders are needed, which may result in increasing the operation time and reducing the throughput of the overall motion system. As stated before, we want to have a reference motion profile with finite jerk values to enhance the tracking and reduce the vibration. but this may take more time with more intervals being involved. We can use three main intervals: acceleration, deceleration, and constant speed. The constant speed interval depends on the operational conditions given, so we can optimize the first and the last intervals. For example, in the acceleration interval, we have two boundaries, the initial and terminal boundaries. We can attach an autonomous linear system to each boundary and make the terminal boundary system go backwards in time and the initial boundary system go forward in time. Having the superposition of these two systems, we can produce the desired reference signal given here as zeta of t. To present a systematic way of dealing with this kind of structure, we desire one system that exhibits two boundary behavior. Luckily, we can utilize the theory of singular perturbation to do that. Adopting singular perturbation theory allows us to introduce the concept of minimum energy into the multi-interval trajectory making process. Also, this helps in obtaining near-optimal trajectories over finite time intervals. Moreover, the two boundary systems are created as time-invariant linear quadratic regulators under singular perturbation, even though the involved matrices in sigma 2 are time-varying. This last feature comes in handy when sigma 1, i.e. the motion system, exhibits a position-dependent behavior. Recalling sigma 2 dynamical model, we are actually interested in making it optimal and autonomous by relying solely on the provided terminal conditions. Therefore, we use the performance index usually attached to linear quadratic regulators, and after introducing scale time variable denoted here by t tilde, that performance index shown here at the very bottom of this slide is actually ready to be optimized using singular perturbation theory. The singularly perturbed version of the trajectory generator system sigma 2 is shown over here, which can in fact be optimized using the provided input u tilde. Also using the co-states dynamics shown over here, the boundary value problem is to be solved after specifying the weighting matrices qi and ri is shown over here. The coming slides are specifically meant to show how this problem can be solved. Defining the transformation shown here, the coupled boundary equation can be decoupled where the two resulting algebraic Riccati equations can be solved numerically using Schur decomposition algorithm, for example. Those are associated with the needed initial and terminal systems we talked about earlier. This theorem is the basis of the proposed approach by which the existence of a near-optimal solution given as the superposition of two linear time invariant and autonomous systems can be proved. Note that the obtained suboptimal solution can be enhanced by reducing epsilon I, which requires increasing the time intervals involved, and therefore affecting the attainable throughput. This can be used to find a relation between optimal performance and possible throughput that can be consulted whenever the machine is actually being operated. Clearly, the terminal conditions of the boundary systems must be clearly specified to completely define the near-optimal solution. Based on the design requirements, these terminal conditions can be found using the equation shown here in the middle. Now the desired reference signal is obtained as planned. Next, let us see how the structure does appear into the tracking error that is meant to be minimized. Having established the existence of the desired reference trajectory structure, now we need to realize its companion system by appropriately choosing its involved matrices AT, BT, CT, QI, and RI, such that the tracking error is minimized to meet any imposed given performance requirements. Moreover, the acceleration and deceleration in time intervals have to be minimized to meet any imposed operational requirements. Note that the constant velocity interval is not usually optimized since it is dictated by the imposed operational requirements. Interestingly, asymmetric reference trajectories can be obtained by simply having the acceleration and deceleration intervals different. Solving the shown optimization problem will be investigated thoroughly in a separate study. To mainly examine the feasibility of the proposed approach, we used a simple double mass spring-Dunbar system as shown here, under the specified design requirements given in Table 1. In this study, we opted to investigate the tracking error when sigma g and sigma 2 are exact replicas under no operational and no kinematical constraints being involved. Note that the matrix conformity was taken into consideration while doing so. These figures show the results of the two-boundary reference signal compared to the second and third order profiles, as well as the sine motion profile. Interestingly, under the simulated example, the sine and two-boundary profiles were almost the same as shown in the previous figures. Also, their performance was almost the same as can be seen from the figure showing the tracking error. Note that the sine profile is a mere signal, while the two-boundary is a signal that is associated with a system that can be adjusted to suppress and hopefully excite any number of involved flexible modes as shown here in the diagram, for example. Therefore, the difference between the two signals is expected to be significant when more flexible modes are involved. To understand the similarity, using Euler identity, the sine signal does in fact exhibit the same structure proposed in this study as can be seen from the provided equation. At the jerk level, zeta 4 can be given as the sum of exponential and trigonometric functions as given in this mathematical expression. In conclusion, this study covered the reference motion design problem from a system theory perspective and not from signal generation perspective. Inspired by the nature of the widely used reference trajectories, three main intervals were identified and utilized. Introducing the concept of boundary behavior, singular perturbation theory was utilized to solve the associated two-boundary problem. Consequently, a preferred structure of the reference trajectory signals emerged, which gives a voice to the motion system to decide upon the desired trajectories it must follow. In this study, no kinematical constraints were involved and only symmetric trajectories were designed. Currently, we are looking into designing asymmetric reference trajectories and the appropriate choice of the involved matrices, along with solving the optimization problem shown earlier. Also, we are looking into ways to suppress excite flexible modes and to deal with position-dependent behaviors of the motion systems in general. Ultimately, we are working towards building an autonomous trajectory generator that is driven by dedicated machine learning algorithms. Thank you.